waiting in another room. So we have just been moved to this one, to the right one. So I guess it is time to start, right? So welcome again to the cycle of conferences entitled Situating Space Technology Between Lab and Field Sciences, sponsored by the Catalan Society for the History of Science and Technology. Yes, before beginning, please note that this meeting is being recorded. So if you don't want to be recorded, I am asking you to kindly leave the room now. Thank you. So this cycle seeks to place satellite technology. It interrogates the relationship between satellite technology and field sciences and natural history practices. We bring together three excellent scholars, experts in different aspects of history of science and technology, and that they all encounter in various ways the question of lab and field borders as it applies to Earth orbiting satellites. Today is the second session. Last Wednesday, it was Christine Harper who lectured. Today will be Sebastian Grevsmühl. And next Wednesday, the last Wednesday, will be Chunglin Va. Again, thank you to all of you to being willing to participate in this conversation. After Sebastian Grevsmühl, Chunglin Va will provide some comments, and then we will open the discussion. As usual, you can leave your question on the chat. You can raise your hand, and even during the discussion, you can express whatever thoughts come to your mind using the chat option. So let me introduce Sebastian. Sebastian Grevsmühl is a CNRS researcher at the Centre de Recherche Historique of the École des Hautes and Sciences Sociales in Paris. He's a historian of science, technology, and environment who specializes in environmental history and visual studies. He has written mainly on the geophysical sciences, environmental history, polar history, and the history of explorations, visual culture, and the role of images and metaphors in science. He's the author of La Terre vue d'un eau, l'invention de l'environnement global in 2014. And it is an honor to have you here, Sebastian. So whenever you are ready, you can begin. Thanks.
Thank you very much, Gemma. Thanks a lot for organizing this cycle of conferences, of three very interesting three talks you organized. Thanks a lot, and thanks a lot to everybody for joining us today on another issue on the field and lab border. Last week we heard Christine Harper talk about the field lab border in meteorology. Today we will talk about something quite related to meteorology, actually, because we'll talk about ozone science in Antarctica. And that research is based mostly on research I did for my PhD thesis, partly, and later on I published some of it in La Terre vue d'en haut, but also on the metaphor of the ozone hole and the images. And I'll basically talk about all of that, and specifically about the field lab border. And the story can be actually told when, now I have to see what you see on your screen. Hang on, I'll just have to gallery. Do you see my my PowerPoint?
No, we are seeing you, Sebastian.
Oh no, okay, I have to share my PowerPoint. Okay, so I will share my PowerPoint. There we go. All right. So this is what we'll talk about, exploring the borders of lab and field sciences. Okay. Yeah, it's okay? Good. And so this story basically can be told in very much about dichotomies. It means we can talk about two radically opposed institutions, the British Antarctic Survey and NASA. We can talk about it as as a way to talk about it's polar science versus space sciences. Or you can talk about it also as something like fundamental sciences versus big science, because the British Antarctic Survey was a lot engaged in fundamental science and ozone science. And NASA, of course, is as the big institution engaged in big science. And so you have also quite different budgets involved. The economies are very different, of course, of the British Antarctic Survey, especially of the ozone group, and of the big science on the other hand at NASA. And you could also talk about it as the opposition between a very sparse field data and a lot of data that you get from space, because the ozone scientists, when they were doing their research in Antarctica, they would have maybe 2 or 3 readings a day, mostly 3 readings a day. And on the other hand, you will have up to 200,000 daily readings of ozone from the satellite. So these are two highly opposed worlds that came together and brought about a new geophysical phenomenon, or brought about new knowledge about a geophysical phenomenon that happens still today every year, the Antarctic ozone hole. So this very same geophysical phenomena, we can have a look at it from 2 different perspectives, 2 broadly opposing scientific traditions. And we will find out where they cross, how they cross, and what that can tell us about field and laboratory sciences in Antarctica. So I will give, this talk will basically be structured a lot around, I will show you a lot of images. Just at the beginning, I will talk about 2 concepts I would like to discuss a bit more. So we'll have a bit of text there, but all the rest will be images. And the text is only there that I don't forget to talk about most of the things that I want to talk about. So let's start with the infrastructural globalism from Paul Edwards. Now, Paul Edwards proposed this concept in A Vast Machine in order to tell us much about why models are so important for the geophysical sciences during the Cold War, how we can make global data and how that data becomes global, and what kind of frictions may be involved between within this process, because mostly when he talks mostly about satellites, and satellites are of course planned in a long time in advance, and you never put the same instrument on the next version of the satellite. So of course, what you want to have an improved new instrument and so on. So there's always friction between each satellite that you put off, because it's never the same instrument. So that on the British side, the British Antarctic Survey, when they were doing their ozone work, they always used the same instrument. So there's no data friction involved. So that's why this concept is quite interesting for our case. But it's also interesting for the 2 other points, for making global data and making data global, because the British Antarctic Survey, when they did their ozone measurements, they did highly local measurements. That's why they didn't talk about the ozone hole when they published their findings. They talked about stratospheric ozone depletion, and they were talking about depletion above Halley Bay. So it was a very local observation. That's what a Dobson spectrophotometer does. It looks vertically up into the sky and measures the vertical column of ozone in the whole atmosphere and stratosphere. So it is a very local observation. But since these observations are connected also to a global ozone network, you get also an idea about global distribution of ozone. Although you get a much better idea with a satellite. So satellites, of course, will give us the global perspective, whereas the British Antarctic Survey will give us a very highly local perspective. And that is also expressed in the way, how the papers were published. It explains also why NASA invented the ozone hole metaphor and not the British Antarctic Survey and so on. But it explains actually many things that we will discover all along this talk. Now, there is another thing that is important for our discussions about the field lab border, and that is the spatial term and the more closer attention that can be paid to space and place within the production of scientific knowledge. That what we call usually the spatial term. And in his book Robert Kohler, in this great book on biology, Landscapes and Labscapes, exploring the lab field border in biology. It's a really interesting book telling you the history about biology and ecology and the borrowings that went on between the lab and field border. And it's very interesting to see that until the 19th century, those two terms they only started to make sense in the 19th century. Before that, you couldn't make that distinction because nobody talked about lab and field in the way we talk about it today. And it's only at the end of the 19th century that it became problematic to borrow from the laboratory in the field, that we would say, these high precision instruments, how can you take them into the field? And will they produce the same things? Is it allowed to do that? And so on. Many questions that were introduced that only happened in the late 19th century. And in the same way in Antarctica, we can observe similar things all along the 20th century, where this distinction between field and lab becomes very problematic. And we will see in this talk, we will see why this has become problematic. It's also interesting because laboratory, is usually considered as completely independent of place, that you could reproduce the experiments anywhere on the world, which is today often not true, and you often don't do that because it's not very boring to reproduce exactly the same thing. But it's also often impossible because the infrastructures, the laboratories we use today are often that complex that you can't really replicate the exact same thing anywhere else. So and the field sciences, by definition, of course, they are engaged in the field, and they are by definition place-bound. And so there is always this tension between this universal reproducibility and the very local specificity. And this tension is very important because it gives different authority to scientists, how they talk about specific places and specific environmental phenomena or geophysical phenomena. And so what you can observe, for example, when you look at the oral history interviews that were made, most notably by the British, at the British Library, the oral history project they have going on there. And you see that the British Antarctic Survey scientists, they're very much connected to place because they always go down to, it's a hard effort to go to Antarctica. It's a very difficult place to conduct science, and they are very attached to place, and they have a big authority when they talk about Antarctic ozone. And it comes also from this difficult engagement with the field. And this is not at all perceived in the same way by the space science community, of course, as we will see. And so there is always this tension that arises automatically between these traditions. However, as we will see, ozone science implies a lot, there are a lot of laboratory-like conditions that are also necessary to produce ozone science. So we will look at this in the following. And that's why in the 20th century, there was this distinction between the lab field border has become problematic, especially in Antarctica, because when you move in the field, you have the place where you study, or let's say all the strategies, the resources you use, the techniques you mobilize in order to guarantee, one could say, the survival of the scientists in the field in this hostile environment. So all these resources, they are of course linked to the strategies and resources needed for the production of the scientific knowledge in Antarctica. So this comes always together. And in this way, I think it is good to think about Antarctica actually as a unique laboratory. And that's how one often talks about Antarctica, especially since the 20th century. Well, actually only since the 20th century. But as a laboratory in an extended sense, meaning you can basically test anything there. It's like a blank space, a white blanket, and you can project a lot of imaginaries, a lot of ideas, a lot of theories on this concept. And that is precisely the case when you think about Antarctica as literally literary laboratory, because a lot of literary imaginaries were projected there along the 18th, 19th century. You have it as a social utopia. You have it also for legal models, because Antarctica, the Antarctic Treaty, is used as a legal model to think outer space and the deep sea, the law of the sea. It is a precedent for all international planning of legal models for international spaces. And of course, that's why it's called Antarctic analogy in the legal sciences. Or you have it also, of course, as a laboratory for political systems, meaning you can test ways of engaging in the Antarctic Treaty. So is, for example, a model to test how can you put territorial claims aside and invent a new model where science is replaces the geopolitical aspects that were very important before that, and that still are, but science is the new currency that with which you can engage in this geopolitical engagement. And so there are plenty of other ways to test or to see Antarctica as a laboratory. Just one tests, of course, space equipment there because of the isolation and the harsh environment. You can test, of course, the psychology of isolation there. You even have Werner von Braun, the founding father of the American space program. He also traveled to Antarctica to see firsthand how do you organize research in a hostile environment, very far from any place in the world where you can where you don't have access to where you have to bring everything with you in order to survive in that environment. So that's why also the Werner von Braun and Studinger and other people from NASA, the early founders of NASA, they traveled also to Antarctica to see firsthand how you can organize these efforts. And and of course today Antarctica is the laboratory to observe global environmental change. So it's a global laboratory in this sense. So why is, let's have a look at Antarctica more closely as it's in its geographical and physical geographical setting. So it is, of course, an extreme environment where you have a lot of ice, on average 3 kilometers of ice. That means you're always, when you work on the continent in Antarctica, you always work at high altitude. And it's not only that it's difficult to work at high altitude, but of course there are also very harsh weather conditions, and half of the year you don't have a lot of light or no light at all. So that means the context is extremely difficult. And upon you could add to that, of course, also the geopolitical context. So, and that you have the different claims here, the different sectors of the different claimant nations you can see here on this map. And if we look at the British claim, which is the wedge on the between 9 and 11 o'clock, this wedge is also overlapping with the Chilean claim and the Argentine claim. And Halley Bay, where the observations were made, is just next to one of the Argentinian bases, scientific stations, and not too far from the German station. So you have always the nations that are claimant nations. They would also put their bases, of course, within their sector to make sure that this claim is maintained, although the claims were put aside by the Antarctic Treaty, of course. So, but that gives you an idea what science in Antarctica, what it means also as a geopolitical, as a geopolitical setting. And science has become since the International Geophysical Year, the main engagement in science. And the International Geophysical Year in 1957, 1958 brought fundamental science to Antarctica, and amongst that, ozone research. And since then, ozone research is done in Antarctica on a highly regular basis. almost without any interruptions. And that is very important for our story, because the British Antarctic Survey is really, and especially this man, Jonathan Shanklin, who published together with Joe Farman and Brian Gardner the famous paper on the ozone depletion. The British Antarctic Survey is the only institution in the world that has an extremely high currency or high authority to talk about ozone in Antarctica. And that is precisely because they, just like the Keeling curve on Mauna Loa in Hawaii, you have the same thing here for ozone, starting also with the International Geophysical Year and going until today, a huge data set, a database that was always done with this instrument, the Dobson spectrophotometer. And this instrument, as I said before, is an instrument that won't show any friction, unlikely the satellite instrument, because this instrument was invented by Gordon Dobson in Oxford in the 20s. And this is his first instrument we still have in London in the Science Museum. And this instrument is basically still the same, only we had right at the beginning, there were photographic plates, but they were, in the late 1920s, they were replaced by photographic cells. And that is the only thing that was really changed about the instrument. And so this is a highly robust instrument you have that doesn't change over time. And there are maybe 150, I think, or so, that were built over the years and that form the ozone net, that are part of the ozone network of this global infrastructure in the sense of Paul Edwards. And what was the outcome of this work now of ozone observations in Antarctica of Jonathan Shanklin, as you can see here, and his ozone Dobson spectrophotometer in Antarctica at Halley Bay. So this instrument was brought down to Antarctica since the International Geophysical Year, as I said, and this is their first publication. And it took them a really long time to publish something on ozone. It took them basically 15 years to publish this report and to tell the public that there's not much to tell. And actually, that is very much what fundamental science is about. You do observations, you think, oh, there might be a connection with meteorology, and it might help us to have much better predictions. It turned out that wasn't the case. And what it turned out, there are variations and there are seasonal variations and so on, but it wasn't really the most exciting stuff to do, and especially not to report, because they had trouble to remain funded, that their funding would be kept up and that they could keep on building this important environmental database. And that is, of course, because, yeah, they had troubles really selling a good story on this, because, of course, there weren't not many stories to be sold. But nobody could foresee that there would be a really big story to be sold in the end. But this is just to give you an idea how they published their reports. These are the findings, the average ozone values that were measured, and they are tabulated in this form. And it sees this is a really robust database. It's highly robust, and this is to show how these are the typical field chart, how you would do the observations. And these are quite complicated observations. You have to be really careful when you select the wavelengths. It says it shows you exactly which number of instrument was used, because each Dobson spectrophotometer has a specific number, is identifiable, and then you have all these calculations that have to be done, and so on. So it's a pretty hard work. And during the late 1970s, the researchers of the British Antarctic Survey, Jonathan Shanklin and Joe Farman, were observing that the ozone values were going down. And here we have Jonathan Shanklin in Antarctica in 1982, bringing down a new instrument to check if the instrument is still calibrated well. So they had other instruments that they calibrated, of course, against against each other, and they would bring down a new instrument to see are the ozone values really going down, or is this just our instrument? And so here you have in the hut, you have the instrument that observed the values going down, and this is the new instrument that he brought down from the British Antarctic Survey from Cambridge. And it produced actually the same readings. So they were sure that what they were observing is ozone depletion above Halley Bay. And that's happening every year, late September, beginning of October, ozone values are going dramatically down. And this more and more so. So Jonathan Shanklin, he wrote to NASA, unfortunately to the wrong people, but he tried to reach them and to reach out and say, hey guys, did you see anything like we do in your satellite data? We are observing ozone values are going down, and values are around 200 Dobson units, which is considerably lower than our 1957-72 average. That's their famous report. And then he would write, we would be interested to know if this is confirmed by satellite data. If so, is it possibly connected with the El Chichon eruption and so on, blah, blah. So this was addressed to the wrong people, the wrong group. They would write back, no, we're not engaged in ozone observations anymore, and so on. So they went on and they published their paper. They didn't get any response, so they didn't get any response from NASA. So they published their famous paper in Nature in 1985 and said there are large losses of ozone above Antarctica. And here is where things really got interesting, because first of all, the paper was published. This is what Jonathan Shanklin, he drew this graph before the paper was published. And then when they sent it out, this is what this graph became. It became, first of all, you can see the abscissa here. It's pretty large. And now we're going over here. Now they shortened the abscissa a lot. So now we have a steep decline. And he connected this also with something else. He connected this also with, he made an inverse correlation actually. On the right-hand side of this graph, so you see here, first of all, you see average values of ozone going down over the years from 1957 until 1980, 84, 85, always going down. From the late 70s onwards, a really steep decline. And then you have next to the graph, you have F11 and F12. And go from top to down, these values are increasing. It's 100 and 200 and 200 and 400 going downwards. And F11 and F12 are the two CFC products that are mostly sold, Freon 11 and Freon 12. Those were the most distributed CFC products at the time. And so they made this correlation. Probably this is linked to Freon 11 and Freon 12, because these concentrations, if they go up, they will go. So that wasn't proven at all, but that was the assumption. And there was another assumption in an interview for the British Library. Joe Farman said, well, we tried to make this really compelling by just putting another graph underneath. We put the February values underneath that below. And then you can see directly with a direct comparison, you can see, okay, this is not happening in February. This is always happening in October. So this is a seasonal phenomenon, and there's clearly something happening there. And that was their most important point, to bring through the message that something really important is happening in Antarctica. What is interesting is that Joe Farman said in that same interview that people weren't really excited about the news. They said there was, from the scientific community, there was little feedback until one guy came around. That was Bob Watson from NASA, a British guy working for NASA. And he called and said, wouldn't you like to come down to the embassy, American embassy, and look at my images that I'm bringing around? I've got satellite pictures of the ozone hole. Would you care to take a look at them? And that's where things got very interesting, because that's the point where NASA comes into the game. And this is where I would like to invite you to switch with me perspective and to have a look at the other side of the story, at the NASA side story of the ozone hole discovery. So when we switch now to the NASA side, here we switch radical the perspective, because now we're moving into space. We're moving on to the Nimbus 7 satellite, and we're moving to the TOMS instrument, the Total Ozone Mapping Spectrophotometer. And just as ozone research in Halley Bay, there are a lot of assumptions that go, of course, into these observations. As I told at the beginning, 150,000 up to 200,000 measurements a day. So those are a lot of readings that are coming in. And they had attached to their different readings on different wavelengths. That's how you measure total ozone. They had attached to that of different profiles, assumptions about how is ozone distributed within the column of the stratosphere and atmosphere, especially stratosphere, of course, like at the height of 10, 15 kilometers, where you have different concentrations. And they had to treat their data, of course, in a very specific way. They had this iterative process how to process their data. And to each process, we have a flag attached. So that means there are certain conditions that have to be met that this data is not flagged and that it can go on. And we work our way down to the production, within the production process of this data processing. So that's how they produced their data of the TOMS instrument. And one of those flags that could show up would be ozone values are below 180 Dobson units, which is basically what the condition of an ozone, where an ozone hole starts from the perspective of today. And this condition, there was a flag attached to this condition. And they actually saw that coming up in the 1980s. In the 1980s, they produced, in 1984, they produced, before the paper from Joe Farman and John Shanklin, they produced actually an ozone hole image for a conference that was held in Prague, a geophysical meeting. And they produced this very first ozone hole map. Although they produced this because they had a lot of anomalies in their data, and they thought, well, it's maybe worthwhile exploring this. And that's where they produced this map with specifically the data that includes also ozone values below 180 Dobson units. And this is what you have in the middle of this this graph, of this map, ozone map of the Antarctic stratosphere, and the whole southern hemisphere here. And this is the first ozone hole map from the 1984, published for that conference. But nobody noticed about really this map. Nobody got to see really this first map, and nobody talked about that really. When people got to talk about ozone was when NASA sent for a press release. They confirmed the British findings, and that was published in the New York Times, where they sent one of their false color maps to Walter Sullivan. Walter Sullivan is the famous journalist of the New York Times who covered also the International Geophysical Year, one of the most famous science writers of the Cold War. And he published this map, and he introduced the term ozone hole, the metaphor of the ozone hole, which from there on took the ozone depletion phenomena to a whole new level, because it introduced this new global imagery of a hole in the ozone layer produced every year above Antarctica. And this made the story really an environmental success story, if I may say so, because I think it powered a lot what would happen during the Montreal Protocol, during the negotiations on the ozone, on the regulation of CFC substances to protect the ozone layer, and the Montreal Protocol of 1987 that was signed to protect the ozone layer and to phase out CFCs. I think, although the negotiators of the Montreal Protocol said that we kept these findings outside of the negotiations because there was a diplomatic strategy of the US, but in reality, you couldn't escape this whole new imagery, because this was all, it was in the press. You would see images on TV and in evening news everywhere. It was basically, it was in a lot of different news outlets. So, and why is this important? Well, this is important because this image, because NASA produced the global image of the ozone, and therefore it produced a powerful global imagery to which they could attach the famous ozone hole metaphor. And they could do this with the isoline tradition, which is a very old tradition, of course, that we know from many geophysical phenomena. We know this from from magnetic cartography, from Halley already from 1701. We have the first isoline maps, but for geomagnetic phenomena. And there's a very long tradition in the geosciences of using contour lines or isolines to predict, to visualize global phenomena. And here NASA uses it for the ozone hole. And it would make its way also into the reports. And Bob Watson, the guy who called Joe Farman to come down to the embassy, the British scientist, he was at the head of all the assessments that were made on ozone, that are the basis of the model for the IPCC later for climate change. So what the ozone assessments were basically the same stuff we're doing today with IPCC for climate change. That's what was first organized for ozone, and Bob Watson was at the head of that. And that's where these images were also introduced. His maps he wanted to show to Joe Farman. These are the examples where this map was also introduced. And it would be also, of course, in the press, but I won't be talking too much about that maybe. What is interesting to see is that in 1985-86, we don't know a lot about the actual causes of the Antarctic ozone hole. And why is that the case? We do know, of course, Sherwood Rowland, Mario Molina, and Paul Crutzen, those three received the Nobel Prize, of course, for their discoveries on ozone depletion and their work in atmospheric chemistry. But they made the link between CFCs and ozone depletion. But what one didn't know, and that was already in the 70s, but what one didn't know in the 80s now, with the ozone hole above Antarctica, what is happening actually in the stratosphere? Why is that happening? There were different hypotheses that had to be tested, and they were tested within different experiments. There were 3 experiments that had to be conducted, and that is where NASA had to move out of its comfort zone, and they had to move out of space science and go into field science, if I can say so, because they had to equip within those 3 experiments, especially the last one, the airborne Antarctic ozone experiment. They had to equip planes, 2 types of planes, one that would fly in the stratosphere, one lower, and this like a passenger machine, the DC-8, that is, you can see you have the overhead lockers and everything, but inside that plane you have all the instruments. So you have the laboratory stuffed into an aeroplane, and that will be used to fly into the field. And the same thing with the Era 2 above the DC, like at the top, you can see it. It is packed with instruments, and basically laboratory instruments, if one can say so. And they will be sent into the field to observe directly what is happening in the Antarctic stratosphere during austral winter in late September, beginning of October. And for that, NASA had to engage and had to cooperate with many other institutions. They couldn't do that on their own, of course. So they had to cooperate with NOAA, with CMA, with NFS, with plenty of other institutions. And that is important for our story, because when you think about the field lab, or about the ways the teams communicated and did not communicate with each other and so on. That's very important, because here we have a collaboration where NASA is moving into a field that they're not so comfortable with usually, because that's not the kind of, well, it's not the main business they usually do. if you would ask the satellite guys, that's certainly not what they will be thinking about. The best way to gain knowledge on the stratosphere wouldn't be to do that, but in order to solve the questions involved in the production or annual production of the ozone hole, that's precisely what had to be done. And it was the only way to test all the hypotheses that were developed. And one was from Susan Solomon. Susan Solomon had the idea that the polar stratospheric clouds in Antarctica that form only in Antarctica when we have very, very low temperature conditions. When the polar vortex is closed, the atmosphere and the stratosphere is sort of blocked during the winter, and the polar stratospheric clouds can form, and there we have heterogeneous chemistry going on that will produce massive ozone loss with CFCs on these clouds, breaking up chlorine released, and then you have catalytic reactions and so on. And so that was sort of Susan Salomon's idea. And this hypothesis was actually tested. It might, for the STS community amongst us, it might sound maybe a bit weird that this old philosophy of science perspective of testing science perspective, testing hypothesis and coming to a conclusion that usually one says that's not what happens very often in science. That's not how science is done very often. But in this case, it was actually the case. And there is one author, a philosopher of science, Maureen Christie. She wrote a book, The Ozone Layer, A Philosophy of Science Perspective. And she explains that in that book very well, actually, how this was done and how these different hypotheses were developed and how they were tested and so on. And a very convincing story, in my opinion. And so another thing NASA learned from this was we have to do better at communicating this idea. And that's why the Goddard Space Flight Center, the center that developed the TOMS instrument and that were producing the images and were getting the data, they decided to introduce the Scientific Visualization Studio in the 90s and to invent environmental or geophysical storytelling. Well, not invent it, but to largely improve their abilities to communicate their findings. And that's where these new ozone hole images came in, or these more these globe-like visualizations of ozone, where you have now a much better sense of how the whole in a more three-dimensional feeling about ozone above Antarctica, and how and they would animate these movies, and they would do ozone hole movies. Although they existed also from the very beginning, they would of course largely improve these visualizations and make a much more compelling visual story to tell the story of ozone in Antarctica. So I guess that was also a very important learning process for NASA in order to engage in better communication strategies in order to talk to the wider public, but also to politics. And so this is also an important lesson from the ozone hole case. And so maybe if I can conclude my talk, I think my time is probably is already I talked a bit longer already than 40 minutes, I believe. So if we want to conclude about a few things in this story, I think it's a good thing, a good way to think about global environmental data is to acknowledge that all this data has very local production places. It means that also, if you look at Goddard, or if you look at the British Antarctic Survey, if you go to Cambridge, these are very local contexts of production that you have to look at very carefully if you want to understand the story. And the dichotomies, if one usually makes between small against big science, of field against laboratory and so on. These dichotomies, maybe they work well to tell the story, but they don't tell us everything about in this story. Because all of these oppositions, they are important for the story, but they don't tell us why it worked in the end, why actually this became such an important environmental success story. Because most of it was produced in the border zones, because that is the case when you conduct science in Antarctica. The knowledge is produced within border zones there. And all the teams that were involved had to engage also in a dialogue, in exchange. Although it was very limited at the beginning, the British Antarctic surveys, they wouldn't get any answer from NASA. And when NASA was looking at ground data for the Goddard Space Flight Team, they were looking for ground data. They couldn't actually find the British observations, because their latest observations, they weren't actually published because the British refused to dilute their data in the global ozone network. The global ozone network is what we call the red books, or what the scientists call the red books. These are books of ozone data that are collected globally for global observations, but they are done with different instruments, different teams, and so on. And the British at some point said, oh, we won't send our data there anymore, because we don't want our data diluted in this science that is not done in a very good way, in their opinion. So they kept their own standards, their own instruments, and their own, and they kept this sort of their own institutional tradition, which only enhanced actually their authority to speak about ozone in Antarctica, because they're the only real experts on ozone in Antarctica. But it also limited a lot the communication capabilities with other communities. And that is basically what we can learn from this story. That what is funny when we look at the NASA doing their field experiments, flying their planes from Punta Arenas into the Antarctic stratosphere, when they do that, they will actually not engage with the British Antarctic Survey. They won't ask the British Antarctic Survey to come in to join them in the field studies. And that is pretty significant for this case, I think, because we have really two institutions that couldn't really communicate with each other, that have their own institutional traditions and so on, and that produce very important findings, but that would be much better off if they would be capable of communicating with each other. And so what we learn basically from this story is that you can build a very robust database. And that's what the database on ozone in Antarctica is for the Halley station, for Halley Bay. But it's no use to have a very robust database if you can't share that data with a wider community. And and on the other hand, you need also a global perspective, of course, to understand the global dynamics of the stratospheric ozone loss in Antarctica every year. And so, yeah, I guess, well, these are just some ideas I have about ozone and field and laboratory work in Antarctica. And yeah, I thank you very much for your attention, and I'll be happy to discuss your questions.
Yes, thank you, Sebastian, for this exciting talk. I have heard this story a number of times, and you manage always to bring something new to it that makes it still more fascinating. So thank you. Now, Chongling, do you want to follow Anne? Please. Thanks.
Thanks, Gemma, for giving me the floor. And I thanks yeah, this presentation, and which is, like Gemma said, it provides new details, very interesting details on a story that, by and large, I thought I knew, but there are always new things or things that I've forgotten and things that I've overlooked. At any rate, I'll present you with some very generic comments that, alas, will not reach to the level of interesting historical detail as you were able to cover. So my comments are brief, and they divide between a comment on the discovery of the ozone hole and on a second comment on like you introduced here very nicely, the demand of experimental ascertainment. And then third, I would briefly raise the historical dimension of well, the ozone hole in particular and field science in general. So about the discovery of the ozone hole, what was it that elevated a mere ozone depletion, the British discovery made in 1985, by the ozone hole, the concept which appeared in a title of a groundbreaking paper by Crutzen et al. In a year later, and we know that this was earlier. The ozone hole was a little earlier mentioned in the New York Times. First, and here I refer to other work of Sebastian that he didn't cover here now in his talk. The concept of the ozone hole was already in existence for several decades, albeit in very different contexts. Like you have written about making astronomical observations and about a Cold War context. So two different contexts in which the ozone hole was already in existence. Apart from the concept of the ozone hole, there was the NASA's technique of drawing contour maps, and it was already established practice, wisdom. And one could say, without the iconography of the contour line, no ozone hole. Recently, Brian Cantwell-Smith, a professor of artificial intelligence, compared a map of the islands in Georgian Bay in Ontario with an aerial photograph of the same area. The map leaves no doubt about what the islands are, but on a photograph, it is much harder to make out where an island ends and the sea begins. It is not even clear how many islands there are. As Cantwell-Smith observes, we live in a world of discrete mesoscale objects. Artificial intelligence cannot produce those objects for us. So it is us who do that, and we do so by bringing our concepts to the world. Put differently, data do not bring out contour maps by themselves. In common scientific parlance, they need to be digitally enhanced, but not even programs that do the enhancing produce the mesoscale objects that we are looking for. The ozone hole, just like similar visual gestalts, embody theory. We may also say that the ozone hole is a theoretical object. Now I move to the critical ascertainment of the existence of visual objects. In classical natural science, whenever we want to verify the existence of a theoretical object, we turn to the laboratory to produce the object under controlled conditions. Obviously, that's not possible here. As Rob Kohler has remarked, and I'm referring to the same book that with which Sebastian waved to all of us, landscapes and landscapes. As Rob Kohler has remarked, the field scientist searches patiently for the spot where nature has performed the experiment for her. Data analysis, then, is not so much producing theory inductively, but is ascertaining whether ceteris paribus clauses have been met. And I would like to add, data analysis can do so only up to a point. At any rate, putting computer scientists in the realm of experimental reasons is giving them a more circumscribed space. We may also look at simulation modeling, a practice which likewise can be seen as experimenting in silico, as some people say, not in vitro, not the real classical laboratory experiment. But now there is a different dimension again, as the historical dimension, and in particular the historical dimension of the ozone hole. And I'm referring yet again to the work of Rob Kohler, when I point out that in reconstructing the coming into existence of the ozone hole above the Antarctic, we are not merely analyzing conditions which could produce an ozone hole anywhere and anytime in a regular and controlled fashion. We are also looking at the historical conditions which made that the ozone hole could manifest itself at this particular time and this particular spot. Natural events are inherently historical. Field sciences have something importantly historical to them. And when they neglect the historical dimension, they would do so at their peril. Thank you.
Well, thank you very much, Jungling, for those great comments and for some new input, actually, because you rightly point at landscapes and landscapes, because I recommend for anybody that reading as to get at grips with how complicated these interactions have become in the 20th century, actually, and how important they have become to understanding what kind of science, how science works in many different fields. Although Rob Kohler, of course, talks a lot about biology, ecology, it also is very highly relevant, of course, for the geophysical sciences as well. I think you probably will be talking about that in your next in your talk next week when you talk about discrete mesoscale objects. Brian Smith refers to, and you said that the embodied that the ozone hole is very much like an embodied theory, of course, and without the contour lines it wouldn't exist, so to speak. And that's, I think it's very important that it's good that you point that out, because we like to think about global environmental objects like very much like they have become highly naturalized to us. They have become naturalized because of the political implications they have, because the ozone hole metaphor is in that case very interesting. You mentioned that there's a longer history, of course, of the metaphor that was used in other contexts before, but once it became this environmental metaphor, it had a whole new dynamic. It brought in a whole new dynamic, actually, and this dynamic has a lot to do with the ways it was visualized, I think, and that's why it is important to think about data and visualizations, what our perception does when we look at these objects, how our brain actually copes with these, and I think another aspect that is important is about these images is that they still have still have many drawbacks as well. One can of course look at the convenience of having a global perspective on the stratosphere, but there are also many drawbacks that come with their global perspective always, because you lose of course the connectedness to experience, to what we as what we can experience and it's very far outside of our human scale. And that's why that's what many of these images stand accused of. And they are, of course, in that sense, very psychologically sterile. And that's something, that's another aspect I think one has to take into account when one thinks about global environmental objects, because they're very far removed from our experience. But the example you gave from the photograph and the map, the difference between photograph and map, that photographs on automatically maps is a very good example. Thank you for that. Yeah.
Yeah.
Thank you. Thank you, Sebastian.
Yeah, thank you, Chungi.
Okay. So please remember the audience. You can also leave your comments or raise your hands. So I do have a question. If anyone, if nobody else has one so far. So because you talk about the importance of storytelling and communicating data or satellite data, also as a form of institutional propaganda for NASA. But so do you think, or do you have examples that suggest that satellite data about environmental ideas or phenomena, such as ozone or CO2 concentration or sea level rise, require or carry with specific ways of communicating or visualizing, as compared to other forms of data gathering, like surface stations or ships or balloons? And if yes, to what extent this necessity or this is linked to the technical nature of the technology, or is more of a choice of those involved in producing and communicating and this data? Thank you.
Okay. Yeah, thank you for that interesting question. So when they, I had a look, I conducted, of course, some interviews, and I had a look at there are also many oral histories out there. And it is difficult to know precisely why, for example, the Goddard Space Flight people, from the Goddard Space Flight Center, why they chose specifically the contour line or the isoline to produce their ozone maps. I think one reason is that they use polar projection. And in the polar projection, you have to use polar projection if you want to show the polar regions. It's the only useful projection. You don't have to use it, but it's the only useful projection in order to show data of that region. It's the most commonly used one. And when you do that, and it explains also actually the sector principle, why we have sectors in Antarctica, why there are wedges. I think it is also closely connected to the polar projection, because that's how the projection works, and it's the most convenient way to divide anything within a polar projection. So if you want to project now, if you want to put data onto that map, I believe the isoline, intuitively what they used, the isoline tradition, it was a pretty good choice, because it spatializes the phenomena very well. It creates surfaces with which you can actually, and with which you can create very good the whole phenomenon. The black hole, for example, is also the very first Jean-Pierre Luminet in 1979, when he did his simulated photograph of a black hole. In that paper, he also used the isoline to visualize the first black hole. So this isolines are very good to depict holes, so to speak. And one could also say the inversely, it's because of the isoline that holes exist. And so that is one point. And that they used false colors to do that was in one oral history interview I read, where two of the scientists, they were discussing, they had their maps, and then they were starting to color in by hand their first maps. And they said, oh, we should do a computer routine for that. I can do that for you, and so on. And that's how they produced their first false color ozone maps with a computer routine. And I won't go into the technical details, but there were some good reasons to do that. And there is a long tradition also within meteorology, of course, and if you are depicting atmospheric or stratospheric phenomena, so there is also a visual tradition, so to speak. There is, as I said, a long-standing cartographic tradition as well, reaching right back to Halley, Edmund Halley in 1701, his first isogon map. But they're also much more recently within meteorology, for example. And now, why? Now you asked also why, if, for example, the Keeling curve. We all know the Keeling curve, it's just a steep rise. It tells two stories, the Keeling curve. The Keeling curve tells also, of course, global ozone concentrations, that they rise from the International Geophysical Year 1957 from 310 ppm to today to 415 ppm. It's a continuous rise. And as I forgot his name. In environmental history, you have a great article on the Keeling curve. And in that article, he says that there are two stories told. One is about the natural history of the curve, meaning it's like the planet breathing. So that's the oscillation of the Keeling curve. And then you have the unnatural side, so to speak, of the curve, meaning that it's always rising. And that is the human, the anthropogenetic force of that curve, so to speak. And these unnatural and this natural history, they come together within the Keeling curve. And I think, and so you could think about the human history also in terms of ppm. So instead of putting down the year numbers, you could also just think about the human history in ppm for CO2 concentration. So that is I think a nice suggestion, of course, but it tells us also something about this curve, that it speaks as a curve, as a global phenomena. With ozone, you have something much more localized. Of course, it's a global phenomena, a global imaginary, but it's of course localized, and it has to be mapped precisely. And that's why, and it has its origin, of course, in a very local reading, in very local observations within on Halley Station in Halley Bay. And that is, I think, a very important aspect of the ozone story. That is, it has a very, just like the Keeling curve really in Mauna Loa, it has a very local story to it. And, but this localness is, counts also for the global perspective, because it's as a regional phenomenon, you have to map it out in that way. So yeah, I think I'm not sure if I really answered your question, but does that answer your question, Gemma?
Yes, partially. But yes, because as you perfectly know, different forms of visualizing may carry different political messages and may have different public impact. So just your insights about why the ozone is a hole, sea level rise is a curve, and not a hole. Maybe it could be also depicted with isolines, or so I don't know if has something to do with the audience, to what these images are meant to be addressed, or I don't know. What are your insights on that?
How to say? Well, it depends on how many variables you want to take into account. So if you, with ozone, you want to have, if you want to know its geographical distribution, it's important to produce those maps as NASA does it. Or if you just want to have a global indicator, just like the CO2, the Keeling curve is enough, of course, but it wouldn't make sense to have. It does make sense, and we also have those maps, of course, but it's you produce something else. You produce another kind of knowledge, of course. More detail is given to the local. That is actually what is happening also with IPCC. Understood that for a long time they had a tradition of moving to the global, to including mostly global perspectives, global climate maps and so on. And now over the recent decade, we're moving much more into local projections, into highly more localized regional models and so on, and into regional depictions, visualizations, which help better engage problems, get a more local perspective into things, and to connect also more to local communities, which are of course always left out of these highly globalized perspectives. And I think that is a very important aspect to think when we're thinking about global environmental images.
Thank you, Sebastian. Now, Christine, do you want to address your question by yourself?
Hello?
Hello? No, Christine, you have your microphone off.
Off, yes, sorry, okay. Even my computer was giving me a note saying your microphone's turned off. Thank you, Sebastian, for your talk. I want to follow up on Gemma's question. So as I was looking through your slides earlier today, it seemed to me that the presentation of the data with the isolines made it appear that the data was extremely certain, as opposed to the graphical presentation, which showed the error bars, which is typical in sciencey kinds of things, okay, that we show the error bars. But the general public sees error bars and thinks in their mind, their data are really shaky. Huh? Yeah. Like, why should I trust this when I can look over here and look, I've got solid lines, and that must mean that they know what they're talking about. So is NASA in this case getting ready to make the case that there is a major problem? And so they're going to accentuate that problem by making it look like the data are extraordinarily solid for public distribution, knowing that the general public is never going to see those graphs with the dots and the error bars that extend from them.
Yeah, that's very good point. Actually, when you think about the Icelandic tradition, its history, you understand very well why it's so good at inventing this uniform and highly confident visual space, in a sense that it creates continuity there where you don't necessarily have continuity. It's as if you've measured really every spot on the map. And it's the same when Alexander von Humboldt, when he introduced his isolines in 1812, 1814, his isotherms, and when he introduced that, for his map of the northern hemisphere, it's almost a northern hemisphere map with a sinuous line like this, different isotherms. And when he introduced that, he used only about 50 readings or something like that. So he selected 50 readings to depict the whole northern hemisphere, the temperature, the average temperature on different isotherms. So you create continuity there and a high confidence in something that is, of course, very weak on a databases behind that. And the same is with the first ozone map NASA produced. They artificially, as I said, you need profiles of the ozone in the vertical distribution of ozone in order to produce those maps. And since they hadn't a profile for below 180 Dobson units, and how they could, they just artificially projected that profile. They produced that. They said, okay, we'll just say this profile should look like that. We will just arbitrarily say it looks like that, and in order to be able to produce our image. And that's what they did. And it's later, when they went back to their data and actually used the new profiles they were given, they saw that it worked actually pretty well, because that visualization technique, it actually hides pretty well the errors you can make within your in your work, so to speak. It's a very powerful visualization technique, and it's also a highly imaginary one, in the sense, not that it's only errors, blah blah. No, not at all. It's very in the sense that it's very it is powerfully psychologically powerful, in a sense. Yeah. So they use that, of course, to now there's just the story with how it was implicated in the political process. That is something I'm investigating at the moment with a colleague of mine, where we're looking at how could this be mobilized within the negotiation process. Although the chief negotiator of the United States says these images, we had to keep them outside of the process, because we didn't know what the outcome would be of all of these experiments in Antarctica. How if we would have something contradicting our predictions and so on, then we would have a weaker basis to have a strong political engagement and a phase out of CFC. So we need the precautionary principle to be the most important principle to follow, and to have a phase out. And we don't need the exact the very confirmation from the field experiments in Antarctica. And so that's something I will look into with a colleague now.
Sebastian,
yeah.
Hello.
Hello.
Am I allowed to speak? Hello.
Yeah.
Yeah, I think you have covered a very wide range, starting from science, technology to philosophy to history. I have taken up the whole thing. Maybe I will communicate to you later. But I have a question now.
Yeah.
That is, this you have again and again highlighted that until and unless there is communication amongst the authorities, and there is communication from the authority to the down, that is to the public, as through New York Times, as it was done at that point of time by Sullivan. Until that happens, how can a knowledge like that of climate change or that of ozone hole, how, if it is not communicated down to the local level at the common popular language, how it can store for innovative ideas? See, I spoke in vernacular in radio about ozone hole in 1986-7, after the ozone hole report was published by UNEP. Some or other, no communication was. See, it may be that our institutional authorities were weak, or I'm not sure of that. I've not done that analysis. I'm only in the reconstructing mode now. But I feel that what you emphasize, that point is very, very important, that you have to communicate effectively by the storytelling format to the people. What's your take on that?
Well, thank you very much for this interesting question. Yeah, I believe that, yeah, indeed, it's especially with environmental issues, of course, that are so important as the ozone hole, and now, of course, with climate change, the communication issue is, of course, extremely important. It is one of the most important parts about the scientific work when it comes to to policy questions, and what can not only policy questions, but also of course what we as a society, or we on a very local level, what can be done. So I think in the ozone case, it was since so as I said, since the 70s, it was we had of course the ozone. In the 70s we had the ozone. First we had the supersonic transportation debate. Then we had the ozone wars about the spray cans, and then came the ozone hole and the Montreal Protocol with its phase out. And the communication side was I think very well understood by NASA, not from early on with their early ozone maps, and especially also with the at Goddard Space Flight Center, when they introduced the scientific visualization studio that professionalized and institutionalized this role in a very important way, because now from then on you have a professional storytelling, some people that are only doing that will take the data and try to produce compelling stories about the environment, about the global environment. And I think that is that is one of the most important moves they made at Goddard Space Flight Center, in order to get the data also into public discussions, especially also in the policy circles.
Thank you very much.
No, thank you.
So does anybody else have some questions for Sebastian or comments? So now it's 5:30, so it's our time to leave if nobody else wants to add something. So thank you, Sebastian, again for this exciting talk. And to all the audience, remember the next week we have Chungling Va, same times, not same place, but in Barcelona at least. So thank you very much, and hope seeing you there.
Thank you very much.
We have to close the meeting.
Thank you.
Bye bye.
Bye bye.